Okay, welcome once again into the class of topology. And for last some days we are doing separation axioms. We have completed the topics of T0 spaces, T1 spaces, T2 spaces, then regular spaces, T3 spaces, normal spaces, T4 spaces, Eurechon's lemma, and many things in separation axiom. Now we are going to cover some more theorems related to completely regular spaces and normality along with the regular spaces. So this is the first theorem today. What we are going to do is write down the statement of the theorem. This is the class CXR of real valued functions you can say real valued continuous functions on a Tikhonov space separates points of X. So this is the first theorem today. What it wants to say that whatever 2 points we take from a Tikhonov space in the class of continuous function that exists, that made if you take a closed set f and a point x not belonging to that set, there will be a function such that f of x will be 0 and f of every point of f will be 1. That there will be a function of that type which will separate the 2 points we have taken. So if you are taking 2 points a and b, so there will be a function such that fa is not equal to fb if a is not equal to b. That is the statement of theorem, and now we will move on to the proof. So look into the proof of this theorem. So what we are given with? We are given with x and it is a Tikhonov space. So let x along with the topology top be a Tikhonov. Tikhonov means T3 and half space. So there is a T3 and half space, Tikhonov space, and let a not equal to b be 2 points of x. What we want? We want a function f such that fa is not equal to fb. We are given that the space is T3 and half. So if a space is T3 and half, that means Tikhonov space, then definitely it is T1. And in a T1 space, we know that every singleton set is a closed set. So singleton set B will be a closed set. So this is a closed set now, and A is a point that does not belong to this set because A is not equal to B. And since the space is T3 and half means T1 as well as completely regular. So this is a completely regular space. In a completely regular space, if you are having a closed set and a point A that does not belong to that closed set, then definitely there exists a continuous function f. And this continuous function f will definitely be from this class. So this function belongs to CXR, the class of continuous functions on a Tikhonov space. So this continuous function, what it will do, it will separate the set singleton set B and the point A. That means f of A will be 0 and f of every point of the closed set will be 1. But in this closed set there is only 1 point. So that means you can say f of B is equal to 1. So fa is 0 and fb is 1 implies that fa is not equal to fb, and that is we wanted to prove that there is a continuous function in the class CXR of the Tikhonov space such that it separates the points. So you have taken 2 different points a and b, and what you have got a function from this class CXR of continuous functions of Tikhonov space which separates these 2 points a and b. That means fa is not equal to fb. So this was our first theorem of the day, and moving on to the next theorem. The next theorem, write down the statement first and then we will move on to the proof of the theorem. So what the statement of the second theorem today is? Write down. The theorem is, it states that show that every metric space is completely regular. That what we want to prove in this theorem. So what we will do, we will take a metric space and then we will prove that it is completely regular by taking a closed set in it and a point x that does not belong to that particular closed set, and then we'll define a function which is continuous, as well as will be a function such that f of that particular point will be 0 and f of that every point of that particular closed set will be equal to 1. So I am starting by taking a matrix space. So let xd be a matrix space. So I have taken a matrix space xd. Let f be a closed set in this matrix space. Let a be a particular point that does not belong to f. Now f is a closed set, a is a particular point that does not belong to this closed set f, and now what we want a function, a continuous function, such that the continuous function is from x to the closed interval 0, 1, and f of a will be 0 and f of every point of f will be 1. So I am going to define a function. Define the function f from x to closed interval 0, 1. So define a function f from x to closed interval 0, 1 by, so I'm going to define it, f of x is equal to d of xa divided by d of xa plus d of xf. What is d of xf here? So d of xf is infimum of d of xb, where b may be any point of this closed interval f. So this is the function f I have defined like this. Now this is a continuous function without any doubt, because it is a rational function. The only thing is, that remains to show is that this function, under this function, f of a is 0 and f of any point of the set f is equal to 1. So let us check if it is true or not. If it is true, then that means we have obtained the function as per our requirement. Otherwise we will have to check something else. So what is f of a now? F of a. So f of x is defined here. Just replace x by a. So you will get d of aa divided by d of aa plus d of af. What is d of aa? Because d is a matrix space, and we know that in a matrix space d of xy is equal to 0 if and only if x is equal to y. So d of aa will become 0. So it is 0 divided by 0 plus, now d of af. D of af will not be 0. Why? Because a does not belong to f. And since a does not belong to f, d of af will be the infimum. But it cannot be 0, because it will be 0 if and only if a belongs to f. Otherwise it cannot be 0. So this is a non-zero quantity. Now 0 divided by a non-zero quantity is 0. So d of f of a is 0. One thing we have proved. Now we have just to prove that for every point of the set f, d of that particular point is 1. So let b be any point, let b be any point of the closed set f. What will be f of b then? So f of b will be, as per the definition of the function, it is d of ba divided by, here you will again get d of ba plus, now d of bf. What will be d of bf? D of bf is infimum of the distance of the points of the set f from the point b. But since b itself belongs to the set f, so infimum will be 0. So this distance is going to be 0. So what you are going to get? dba divided by dba. So dba divided by dba is 1. That means whatever the point b you are going to take from the set, this closed set f, your f of b is coming to be 0. That means this function f is a continuous function such that f of a is 0 and f of every point of the set f is going to be 1, and that makes this topological space completely regular. So this was the second theorem of the day, and now I am going to move on the next theorem. So the next theorem on complete regularity. So first write down the statement of the theorem. Statement is prove that complete regularity is a topological property. That means we want to show that homeomorphic image of a completely regular space is again completely regular. That is what we want to prove. So I'm going to start by taking a completely regular space X top and its homeomorphic image Y rho, and then I will show that Y rho is also completely regular. So let X top be a completely regular space and let F from X top to another space Y rho be a homeomorphism. That means your Y rho is homeomorphic image of this topological space X top. If it is homeomorphic image, then it means the function f is 1, 1, it is onto, it is continuous, and its inverse is also continuous. That means f is continuous as well as f inverse is continuous. Now what we have to show? We have to show that Y rho is also a completely regular space. X tau is given to be a completely regular space. So to prove that Y rho is a completely regular space, what we have to do? We will take a closed set here and we will take a point that is not belonging to that particular closed set, and then we will try to find a continuous function from this space Y rho to the closed interval 0, 1 such that f of that particular point that we have taken that does not belong to the closed set, it is 0, and f of every point of that particular closed set is equal to 1. If we are successful in doing all this, then this Y rho will become a completely regular space. So let us start. So let f be a closed, so better if I'll say it is a row closed set. Row closed set means it is a closed set in the topology row, in Y row, and let A be a particular point that does not belong to F. Now I have taken a closed set, row closed set, and a point A that does not belong to F, and now I want to find a continuous function from Y rho to closed interval 0, 1 such that f of that particular point A is 0 and f of every point of the closed set f is 1. So how to obtain that? Here this is a homeomorphism. So if f is there, f is closed, then inverse image of f under this function f will also be closed. So this means your f inverse f is tau closed. It is tau closed. And A does not belong to F. A does not belong to F means your F inverse A does not belong to F inverse F. So what we have done basically, we have transformed everything from here to here. And this space is given to be completely regular. And in this completely regular space, now we are having a closed set and a particular point that does not belong to that particular closed set. Since it is completely regular, there must be a continuous function from X to closed interval 0, 1 satisfying the given condition. So therefore, there exists a continuous function, I am naming it as G, from X to closed interval 0, 1 such that G of that particular point, the particular point here is F inverse A. So G of F inverse A is going to be 0, and G of this particular set, G of F inverse F is going to be the singleton set 1. Now, this G of F inverse A, you can write F inverse composite with G, A is 0, and you can write here once again F inverse composite G of the closed set F is equal to 1. Now, the main point lies here. Your function G is continuous. Since F is a homeomorphism, F is continuous as well as F inverse is continuous. So F inverse is also continuous. If F inverse is continuous, G is continuous, then we know that composition of two continuous functions is a continuous function. That means f inverse composition with g is also a continuous function. So what you have obtained? You have obtained a continuous function f inverse composition g, and this function is from where to where? This is from y to closed interval 0, 1. So from y to closed interval 0, 1, you have obtained a continuous function f inverse composition with g such that image of the point A that does not belong to the closed set f is going to be 0, and image of every point of the closed set f is going to be 1, and that is the definition of complete regularity that makes your space y rho a completely regular space. So this was the third theorem of the day, and now we are moving on to another theorem, another result from complete regularity. So note down the next one. The next one is actually what we have with the definition. In the definition of completely regular space, we are having that there is a closed set and there is a point that does not belong to that closed set, and then there exists a function, continuous function f, such that f of that particular point is 0 and f of every point of that particular closed set is 1. But this 0 and 1 can be reversed also. That means you may be asked in the examination this question. I am going to write it here for you. So a topological space is completely regular if and only if for every closed set f and for every a not belonging to that particular set f, there exists a continuous function g from x to the closed interval 0, 1 such that, now I am inverting the condition, that means g of that particular point A, earlier it was equal to 0, now I am making it as 1, and g of that particular set, that means for every point of that particular set f, earlier it was the singleton set 0, now singleton set 1, now I am making it as the singleton set 0. And the proof is very easy, because this question, why I am taking it here, because sometimes it appears in the examination and students confuses that the statement is wrong. Here it should be 0 and here it should be 1. No, it can be reversed, it can be inverted. It may be 1 here, it may be 0 here, and the proof is very easy. You are just to invert your function, you are just to convert your function in one step and you will get this definition. So how to do it? Solution. I am not going to full detail of this solution, because in CR, in complete regularity, you know one particular thing, that there exists a continuous function f from x to the closed interval 0, 1 such that f of the particular point A is 0 and f of every point of that particular closed set is 1. This is well known to you. Now just you have to do one thing. Define a function g from x to the closed interval 0, 1 by g is equal to 1 minus f. That's all. Here your theorem finishes. So since f is continuous, 1 minus f is obviously continuous. So g is a continuous function without any doubt. And what about g of a now? So g of a is 1 minus f of a. That means a minus 1. This is not actually 1. This is identity. This is not identity function. This 1 is a function that converted every point to 1. So 1 of a is 1. 1 of a is 1. This is a constant function. And minus f of a. What is f of a? F of a is 0. So 1 minus 0 is 1. And for every point b belonging to that particular set f, g of f, you can say, will be 1 minus f of f. So what you will get, since this 1 is converting every point to 1, so 1 of f will be 1. And f of f is the singleton set 1. So 1 minus singleton set 1 will give you the singleton set 0, and your conditions will be inverted. Now you will get here 1 and here 0. So this is an important example. If it appears in the examinations, you can convert the function, you can invert the function, and you can complete this theorem just by defining one function g, that is 1 minus fa, where 1 converted every point of the set x to the 1. It is a constant function. And one more theorem. What I'm going to take today is theorem is prove that every T4 space is completely regular. Every T4 space is completely regular. So once it is completely regular, it will automatically be taken off. It will be T3 and half. Why? Because T4 means T1 also. So it is T1. If it will become TR, so T1 plus CR will become taken off. That means T3 and half. So you can, this theorem can also be appeared in your examination, where you can get here T3 and half instead of having CR. But here I am going to prove that every T4 space is CR space, completely regular space. So T3 and half will be automatically covered because T4 includes T1. Now, to prove this theorem, what we have to do, once again, we have to show that the space is CR. And to prove a space to be CR, where we have to start with? We have to take a closed set F and a point X that does not belong to that closed set F. So let F be a closed set and let X be a point such that X does not belong to F. Now the theorem starts. Your given topological space is T4. So T4 means normal and T1. So it is T1. And in a T1 space, we know that every singleton set is closed. So this point X, I am going to consider singleton set X. So it is a closed set. Why closed set? Because it is a singleton set. It is a T4 space. T4 means T1. And in a T1 space, every singleton set is closed. So it is a closed set. And since X does not belong to F, its intersection with F will be phi. F is also a closed set. So this is a closed set, this is a closed set, their intersection is phi. That means it is a pair of disjoint closed set. Once again, this is T4. T4 means T1 and T4 means normal. From T4, T1 shift we have used. Now T4, it is normal. In a normal space, if you are having a pair of disjoint closed sets, then by Urysohn's lemma, therefore by Urysohn's lemma, there exists a continuous function f from x to the closed interval 0, 1 such that f of every point of the first set, but in the first set there is only one point, so you can say f of x is equal to 0. Instead of writing like this, I have just written this f of x is 0 and f of f is 1, the singleton set. And is it not the definition of complete regularity? You have taken a closed set, you have taken a point x not belonging to that closed set, and you have obtained a continuous function f from x to closed interval 0, 1, under which the image of the point x is 0 and image of every point of the closed set f is going to be 1. And this is the definition of complete regularity. So your space X star is a completely regular space. And before leaving you here, the last theorem, I am going to prove it for you in this video. And after that, we will move on to in the next video to the complete normal spaces. So in complete regularity, I have already proved that complete regularity is a hereditary property. It is a topological property, and this is one more theorem here. So note down the theorem statement of the theorem first, and then we'll move on to the proof. A topological space X star is normal, or you can say a normal topological space. I'm changing the statement of the theorem. A normal topological space is completely regular if and only if it is regular. If and only if it is regular. So that means what you have to show. Once you will take normal and complete regular, and you will prove that it is a regular space, and that I am not going to prove. Why? Because in the previous video you have seen that every completely regular space is regular. So no need of using this normality. Only complete regularity will make the space regular. So one way, it is already proved in the previous video, and the other way we will have to prove. The other way means you are having a normal space, you are having a regular space, and you are to prove that it is a complete regular space. So for that, I am going on to the proof now. What we are given with now, we are given with that a topological space is normal as well as regular. So let X top be normal and regular. And what we are to show? We are to show that X top is completely regular. To show that it is a completely regular space, from where we are to start, once again we are to take a closed set F and a point X that does not belong to that closed set. So let F be a closed set and X be a point not belonging to that closed set. X is not in F. So if X is not in F, where it is? It is in the complement of F. So this means X belongs to the F complement. So what you are having now, an open set, F complement, because F was closed, an open set and a point X belonging to that particular open set, and the space is regular, given. So you know that if there is an open set G and a point X belonging to G and the space is regular, then always there exists an open set H such that X belongs to H. H is a subset of H bar and H bar is a subset of G. That theorem I am going to use it here. So therefore, there exists an open set H such that X belongs to H, H is a subset of H bar, and H bar is a subset of F complement. Now, H bar is a subset of F complement. H bar is a subset of F complement means H bar intersection with F is phi. Now, H bar is a closed set because closure of every set is closed. F is also closed. This is a closed set, this is a closed set, and their intersection is phi. That means we are having a pair of disjoint closed sets. And once we are having a pair of disjoint closed set in a normal space, we can apply Urysohn's lemma. So therefore, by using Urysohn's lemma, we can say that there exists a continuous function f from x to 0, 1 closed interval such that, now the condition of the Urysohn's lemma, says that f of every point of the first set h bar is 0 and f of every second set, point of every second set, f of f is going to be singleton set 1. Here it is singleton set 0 and there it is singleton set 1. Now, once again, your x, look at x, your x belongs to h bar. And since f of every point of h bar is 0, so why not f of x is 0? F of x will automatically be 0. So this means f of x is 0 and f of every point of the closed set f is singleton set 1. So look at the beauty. From where you have started, you have taken a closed set f and a point x not belonging to f, and now you have obtained a continuous function from x to the closed interval 0, 1 such that f of the point x is 0, image of x is 0, and image of every point of the closed set f is 1. And that is the definition of complete regularity. That means the space is completely regular. So here I am going to stop this video. In the next video, we will see theorems related to complete normal spaces, and T's extension theorem is coming very soon. Thank you once again.